Okay, so welcome everyone to this new episode of EagleFly, the experimental debugger. Today we will continue making this awesome debugger, and if you'd like to follow along, please don't hesitate and welcome. Today we will continue making the disassembler, and if you have any questions, you can post them on Twitter or YouTube, and I'll be there to answer. Okay, so let's start. Close all this stuff. There we go. Alright, so let's compile this. If I remember, we didn't finish it last time, so we're gonna just crash out ahead if we run this. So let's go and run this so we can just crash out of it. So because we just did a little change there, if we can. Oh my god. Yeah, what I was Are you serious? You cannot update the window? This is funny. Alright, so yeah, we did this thing that we didn't finish at all, which was like the way the access and get the names was something that we didn't finish at all, you know. So if you remember, get register name, well, it didn't do anything. So if we run it, we pretty much are gonna do anything at all, you know. We're not gonna print any registers. Pretty much is, there you go. And yeah, we're gonna push something that we didn't get at all. So yeah, so that's normal. So let's implement this, okay? So the first thing I would like to notice here is that, well, the thing that we define here, where we have a modern byte, we have a rec type now. This rec type is something that it's gonna be useful for us in the sense that if you remember, well, I don't know, I think, well, it's already gone. Oh, it's here. So we have this. If we want to fetch the modern byte, we want to fetch the SIB byte, stuff like that, which is okay, you know. I mean, this is something that the data information tells us about. I mean, the modern direct tells has in the encoding itself this kind of useful thing, you know. So it's not like we don't need it, but this. It was the thing, but now it's, since we need to to transform it, you know. And in fact, I mean, I was like always like, since we don't use it, like I I was always tempted to like not make another call of it because it's just like the same thing. But you know, it's yeah, you got the idea. I mean, the whole purpose of this is just to find out the data information. So we're gonna have a, I don't know, something like this. So yeah, I mean, this is a kind of thing like how to use everything, how to make everything. Okay, whatever. Let's go back to the thing we got first. So yeah, this compression, if we see later that it's useful, which for now it's just not a thing. So we need the row index by itself because I mean the tables have like that kind of, I mean, they have some meaning. It's like, hey, you have to fetch something using this, you know, like hey hey, you're using this row index depending on if you have a fetch model in byte or fetch in field, whatever, which is the thing that we have here. That's okay, but now we have to add the x64 thing. So I think what I like to do is to keep the row index, because the row index is kind of useful, you know, even no, I know what to do. I know what to do. I'm gonna keep it there, and then I'm gonna say this is instead of row index, like this. Here we go. We'll call it the offset, and then instead of doing this, we're gonna say that this thing right here. and that's all she said. Now you are here, Alex, implement. Okay. Yeah, and we can just say and we have the modern by thing, which we passed already, so that's gonna work. And this is the rec type, which is the thing right here, and the rec by. Now our rec by, we're gonna do something special. Let me just erase this stuff, and pretty much we pretty much want to do the same stuff here, you know, with the EIs. Yeah, I mean, this is all we need, isn't it? So if that's what we want to do, we have to make some transformations on the data set. So we go to disassembling. Instead of using the data size because it was not super useful, we need some data type that we can use. Now probably, I mean, here also we're missing the data size, because the data size is going to tell us, at least for some of them, it's going to change that information. Okay, so here is missing the data size. Well, not necessarily, because it's because the operand size override thing is gonna change the thing, yeah. Sometimes we use the effective operand size. So if we pass the effective operand size, which is here, we have to make the combination of it. So we still need the effective operand size here, and the reason is because sometimes, I mean, we cannot just encode the data type or the data direct type in the enter group. I mean, it's something that we already have by itself, you know, like, but we don't have it explicitly. We just have this size, a size here, you know, which is like data size effective, data size, that kind of stuff. But since the resolution of the data size needs to be made on the computation itself, because we need to first see if there's an override prefix that makes some changes into it, you know. So I think that, oh my god, yeah, that's important in that case. So here I'm gonna say, well, pass me the effective open size, and I'm gonna play around with it, which, yeah, I mean, that's the bit scan forward thing. So probably it was bit scan reverse, I guess. No, bit scan forward. There you go. And instead of having the bit scan forward, we can just say I mean, what I want to say, I want to say this. Yeah, we're gonna need the rect tag by itself. We're gonna need here the effective operand size, or the size, which is in this case, I'm gonna call it operand size, but it can be anything, operand size, and then I'm gonna go to tables, and right now what we do with the operand size is that data size, we have this kind of stuff, 1 2 3 4 5 6. $64. Well, probably it's the same thing, the bit scan forward thing. It's just like because you just need to do the same stuff. So then I'm gonna say this: if well, we can use any of these because it's gonna give us the offset from the same value, so we can use this one as well. And we can assert that the offset type can rect type normal info, and then we can say plus info offset plus offset. Yeah, I mean, if it's 0, then it's gonna be adding nothing. So yeah, and then now we can say, well, the REX type is just gonna be we have to use REX by as well. And I was like trying to think, but yeah, we can say this: if else if we go which is kind of the same thing that we had before, which is kind of funny. So it's okay. I just want to see, because I erased that part, so yeah, that was wrong for me because it was pretty much the same thing that we had before, but whatever. So we have the rect type. Let's see, what can we do here? We have rex by. If rex by, we can just say that we're gonna play around with it. You know, we have an offset, so we can just use the same offset. Now yeah. Yeah, okay. It's gonna be something, I don't know, whatever. And then we're gonna say we need a base, and then we're gonna say we're gonna need this stuff. Okay. Which we can pass it, or we can just do the same stuff, I guess. So let's compile this. Result, what's this? Yeah, I mean, I'm gonna define the offsetting volume. And we can say type entry, how do you call it? Rec entry, rec entry, rec entry base. Rec spy, and this is going to be there. There you go, we have them. And we can just say So I'm gonna define it here. Of course, we're gonna do this. So let's think about this for a moment. So this was pretty much the thing we had before, and now I want to use the REX by to define the information, you know. So I'm gonna say this goes on the rec. That means that if we go and fetch the modern field, which is alright, I mean this is okay, this is something that should be done. The only thing that we have to do is just to extend it with the REX, you know. So the REX I'm gonna call this Let me remember where we're using this stuff. So it was at the beginning. The REX bit was like we wanna have like the possibility to decide whether one bit is useful or one bit is not. I mean, where does the extension goes, you know? So that, and we have many, well, you have different options here. So we have the, let me go here. Remember that the R field goes to the rec, you know? So whenever we go and fetch to the rec, and we have the REX, we just modify the index, you know? So it's like if we were having this like here, and say, hey, you know, if we have an REX, we do something. If we don't have an REX, we do something else. So the shifting of the rec and field, this is the same. We just need to add the R bit. You know, if we have REX, and we can just do even like this, you know, if REX, we're gonna just decompose everyone, you know, we're gonna have the R, we're gonna have the G, well, it's R, X, and B, so R, X, and B, and even the W probably. Yeah, R, X, B, W, B. Three, two, one. We can just do that. We can say, hey, we're gonna have our REX blah 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 blah, and here we say, hey, you know, if we're gonna fetch the motherm, okay, what the motherm cares about? Well, it cares for the rec and it cares for the RM. Okay, so we can just say that if we have R bit, then we can just play around with it. It's gonna be, this is the same, but you just have to change the base, you know. And like, let's say if, and that's all she says, isn't it? And that's all she said. Okay, I like that. And it will be the same for the others. So, and this can be if rec type id equal rec type normal. And we get the offset. Okay, I like that. I like that. And of course, well, this is gonna be now if we are fetching the, well, here more precisely, if we are fetching the arm field, which is something, not fetching the arm field, let's say, and we have the R field, then we do this, and the offset equal to the rec. And if not, the offset equal to the RM. And we have here the bit, or what is just the bit, isn't it? Yeah, the bit. It's gonna be the same. Then we'll need this, and then we're gonna say we don't have the rect type initialized, so let's do that. Sorry. So where did we find? We don't have rect type at all. Oh yeah, we have it. Well, well, we have to define it, and it's just gonna be the rect type. It's gonna have and I believe we have something. Well, we can just forget about it. Well, whatever. Yeah, it was, I don't know if it was here, it was on enum, or it was on the tables. Here it is, the raised of type. Okay, so we need this thing here, Yeah. I mean, we can just say register groups as well. And in fact, while we have the groups, do you remember that we had a group thing here? Can we use the same thing? Yeah, I mean, we could, but for now I'm gonna keep it there, and later we're gonna compress it, if that's the thing. So we can just say the register group, whatever. And here I'm gonna say that I want on the CPP, we got it, the base, the count, and the type, and this is gonna be EagleFly register type. Okay. There you go. And if that's the case, I think we don't need this anymore. So I need to pass on the disassembly tables. I'm gonna call it normally like this. And this has a register type. It's not gonna have a register type, it's gonna have a register group. Well, in fact, we can have a register type. I prefer it. These are for in place of register encoding and explain by instruction. And then we're gonna have, this is gonna have a bunch of offsets, you know. So just as the same way we have the entries, we can just say the same thing for the registers, which I think it's nice. So let's compile that, and here we're gonna say that this is a group, and this is gonna be a rec group, rec group, rec group, group, rec group, group, rec group, rec group, rec group, rec group, rec group, rec group. There you go. Compile again, and here we have a rec group theme. Of course, the entry has a rec type, so we're gonna say this rec group type equal blah, rec group base equal to this has some state rec groups rec group type well, pretty much this is the thing. You can just say this and all these bananas go like this, and yeah, there you go. Okay, so we're gonna have a rec group, compile, It's gonna tell me, oh, you don't have rec groups. Okay, doesn't matter. Compiler, thank you very much for telling me that. Because I'm gonna just say the same stuff, yeah. So EagleFly register groups, rec groups, and we're gonna have where is it? On the table where we have a type, I want to have a rec type count thing, and pretty much do the same thing there. Table rec count, table recs 1024, and that's all she said. Well, this goes right here. And here REX is a pointer, isn't it? Okay, so we just reference it. And here I'm going to set a type. I'm going to say rec register rec type REX. Okay, rec type REX. Okay, there you go. This is gonna be something, I don't know, whatever. This is gonna be rec type. This is type. This is gonna be the base. Doesn't matter. This is type. Type. This is gonna be where is the operand size? Did we change that? They should have an operand size, eh? Here we go, we have an effective operand size. Oh my god. That was bananas. Oh, is the size, okay. Operand size. Operand size. Compile. Cannot add to pointers. That's correct. Let me see. So probably I prefer this to be, where is it on the tables here. Disassemble. Well, I could probably put it on disassemble. It's because we have the group here. I'm gonna put it here because hey, look at this. And this is gonna be memory index base whatever. And here we're gonna say that we need a name. This is gonna be EagleFly so it needs this stuff, buffer size, so what's the problem? Do we have an extra comma? Does not take 3 arguments. So do you think we are passing 3 arguments? We are passing 4. No, we're passing 5. That's kind of weird. That is kind of weird. Buffer again. Buffer size, rec name text, dude, that's super weird. Well, probably it's because we haven't solved this problem. Okay, so this is gonna be I mean, we don't even need this, you know, rec group equal disassembly state rec groups and that's all she said. Now this should be like this. This should be like this. Left of text. Oh, because we have a pointer to it. Okay. Potentially initialize variable. Oh my god. Okay. Rbit bbit use. Okay, thank you. Thank you, Mr. Compiler. You are the best. There you go. So we already changed this stuff a little bit, so it's more useful now. It's more useful. We have to change also the SIB, but we already just hold me a second, so we can just make this stuff happen, you know. So if we run it, of course we have to change the tables as well, so it's useful. So in fact, well, let's do that now. Well, let's run it. I want to see how it crashes. So let me see here. Let me see, cbyte, mandatory prefix. We have an REX, yes we do, effective operand size, blah 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 blah. Get a mnemonic entry, well, okay, we can go there. We have a move instruction, yes we do. It doesn't have a rect to mother m, it has a mother m present, blah 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 blah. And then operation mode 0x03, immediate size invalid, memory operand size, data size invalid, register operand size, data size. Okay, this is all working correctly. So we can just say, hey, we go there and we go fetch the memory operand, which is in this case, I don't remember which was the instruction. Let me see under disassembly. We add the array. Well, it's the array door pointer EAX004. Okay, so it's a memory thing. Okay, so we have to go for a memory thing there. And we're gonna fetch the register operand with an index size of 4. That's correct. So that's correct. So we should go and get EAX. So we're gonna say, well, what's going on here? We don't get it. This is gonna be bananas because it's just nothing. Well, yeah, it's bananas. And if REX, we do have REX, we just and we have an R bit of true, W bit of 0, X bit of 0, and B bit of 0. That's correct. Rec rm fetch rm field. Are we going for the SIB? No, sorry, we're going for the arm field. Yeah, no, we're going for the oh no, that's correct because it has to be EAX. Okay, so we don't have B bit, that's correct. Offset RM, else whatever, assert offset rec group, and here is the assertion. So yeah, let's do the rec group stuff and stuff. We haven't set the count at all, so we just cannot say anything about it. So let's initialize all that stuff. So for that, I would like to go to the table stuff here, and if you remember, this is the thing to do. You have to change table initializer. So that's what we're pretty much gonna do here. So let's do that. So the first thing I'd like to do is that, well, the disassembly state is going to be pretty similar to this stuff, you know, what we have here. But this is for the entry thing, so we can just do the same thing for the other stuff as well. Alright, so we can just copy this like that, and we can just say that we have that. So we're gonna say, well, first of all, I am gonna say that we are gonna iterate across the rec groups to initialize them, you know, and then I'm gonna iterate across the tables, the table itself, you know. So we are gonna, okay, so group index, array count, group infos. In this case, it's gonna be rec name scan. Thing that we got it, and then like that, like this, and then here, well, I can say rec index, and here I am gonna say EagleFly rec group. Well, what can I say? Can do this, I guess. And group index equals 0, index less than array can, disassembly state rec groups, plus group index disassembly state rec groups plus disassembly state rec group disassembly state rec, well, no, group index and let me pass this as well to the tables. There you go. And here we can just say that this is going to be the same. So here we just say, well, you know, I'm going to have that, and then I can play around. We'll have that. What's going on here? We don't need this anymore. I just get rid of this. Doesn't matter. And this is gonna be like this. And the rec group, of course, I'm gonna say rec group type equal to group index rec group. Well, this is rec the how do you call it, rec type count. There you go. This is gonna be the base, and this is gonna be the count. Alright, so the base is gonna be just group index as well. Well, no, this is rec index, which is something that we're gonna use here, and I'll go with that. I can just do that. Well, it can be called rec. Well, I'm gonna do this index. And for the count, normally, well, the thing that we had before is that, where is it? On the table here, we just have 1, 2, 3, 4, 5, 6, 7, 8. Normally, it's about, oh my god, 8. I don't think. Well. That would be pretty much the normal case scenario, but I think for the way we are doing the accessing, we have to I mean, the normal thing is gonna be, you know, from here to here, it has to be one group. You know, this is another group, this is another group, another group, another group. So we can just say that, I mean, this is because the way that we have ordered it, but it's just the same. In fact, we should change this, because we have to, I mean, I'm going to transpose the metrics here, so we can add it in the way we're doing it. So if we are doing it that way, I want to say, but that's going to be the last thing we do. So I'm gonna say here, we're gonna go I can say rec names can, well, rec groups can three, four, 5 times 8, and then 8 rect type can 8 I don't know how many they are. Tables, you can tell me how many they are. 1, 2, 3, 4, 5. and that's pretty much it. Well, it's gonna be, this is 2 times 8, and the others are 8s. Okay, so rec group scan, and the rec field has, I prefer to have it this way, I guess. Yeah. So for the type, we have normally is gonna be well, probably doesn't need it anymore, isn't it? Oh no, it was the data size. Okay, data size. Okay, this is not gonna be size. So we're using size at all? Were we using size at all? So let's see, I have no idea. We were not at all, isn't it? I mean, the size comes from the open size, but that's all. We don't care about the size at all. We just care about the type. Okay, so that's good. So that mean that we don't need this anymore. So we can just say that we're gonna have this table fact. I mean, I don't know if you want to say, yeah, we don't need the size at all. If I have names table. And this can be pretty much the same thing here. Alright, so now we compile. So I think that's all we need to do. Just to get that transformation. And that's all. And that way we can just get rid of this. And their stuff is gonna be the same. I guess we have this stuff, table REX, before blah blah blah. and that's all. Okay. Alright. Alright. So yeah. So let's see what happens. So let's go, I want to go to initialize, how do you call it? No. Initialize subtable. There we got a pointer there. There you go. And let's see what happens. So if we go on the stack, this is 1 2 3 4 5 2 1 2 1 1 1 1. Okay. And right now we have normal, and let me see if the order is the same, because that's another problem. Tables, we have, no, it's not the same. So we need, oh my god, we need it control and then debug. Okay, and then let's see. Oh, and the table, of course, is just bananas, so let me change it as well. The thing that we say that we want to change it, but at the last, so this is the last time. So we need to transpose the table. So it's just gonna be transpose the table, please. This way. This is the way. There we go. There we go. And then there we go. Oh yeah. We have the age. We have pH. And then we need CX, we need DX, we need BX, we need SP, B, we need SI, we need BI, we need EAX, we need ECX, we need EDX, we need ABX, we need ESP, we need EBP, We need EVI. We need MN1, MN2, MN3, MN4, MN5, MN6, MN7, XMN1, XMN2, XMN3, XMN4, XMN5, XMN6, XMN7, and we're almost there. So there you go. Yeah, I think that's all. So now let's go back in here, run this. We're gonna initialize this, blah 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 blah, and we have 5. Okay, that's correct. So we're gonna go for the first one, and the type is gonna be blah blah blah, and the base is gonna be blah 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 blah. First one is gonna be the normal thing, and this is gonna be from the count. How many count do we have? 28. That means 8 times 5. It's 0x28. Okay. It's gonna be 40. Yeah. And then I can just say that this is gonna be the same. I'm gonna get the rec name is gonna be AL, rec count is gonna be whatever, and we just go moving along. This is BL, that's correct. So if we go here to the rec group, I can see that I have a count, a base, and we have a problem here because I mean this is a type normal, the base is, the count is 0 and the base is blah. Here the count is 16 and the base is 40. Here the count is 8 and the base is 8. So it seems like rec index was not added after all. And it seems like if it was adding and then we oh, I see the problem. I see the problem. Yeah, this is not correct. This is not correct. Let's go like this. There you go. So now we go there and we say the rec groups. There you go, that seems more logical. 56, 64, 72. And we don't have a rec count. That means that that's something that we also are missing. So if we do it this way, we're doing the same. But now we have the rectangle correct, which is 80, and the table REX is just gonna have the date information: AL, CL, DL, BLH, GH, blah blah blah, CX, DX, BX, SP, VP, SI, DI, EAX, ECX, EDX, EVX, ESP, EVP, ESI, EDI, MM0, MM1, MM blah 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 blah, XMM0, RAX, RCX, RDX, RBX, RSP, RBP, RSI, RDI, R8 through R15, 00 through R7, 00 through R7, and the others are no. So yeah, that's pretty much it. And this is other stuff we don't care about right now. So yeah, with that thing done, we can do the other stuff as well. The entry count is going to be the same stuff. We don't need to do anything special with that. And they are totally independent, I say. Yeah. Okay. So I can just say, let's go, there you go. We get a C byte. C byte is 68. Why does the C byte is 60? Oh yeah, because it's hexadecimal. CX44, that's correct. That's totally correct. We got REX, we got the RXFly, we're gonna pass it along the thing. It's about mnemonic, there you go. Begin operand extraction. There you go, let's go and do this, fetch memory operand. We're gonna do this stuff, there you go. We don't have an SIB, and here we're gonna have to pass the index size. The operand size 4. There you go, we go and do this stuff and say, hey, you know, we got the REX, there you go. Make the decomposition, and we do this stuff. We're going for the RM, you know, so we're going for the other stuff, and the offset is going to be the RM. And you know, the record type in this case, it wasn't modified at all, so we just go for the info, and the info tells us that we have an offset of 2 from the base, you know, and we have a base of 0 and an offset of 2 and an offset of 0. That's interesting. Well, yeah, that makes sense. Now, if that's the case, this is not gonna be correct because I mean, well, you see here, we're gonna go for Turbo REX. We have to go for EAX, but EAX is a little bit longer, you know, it has to be on 1-0. So it is not going to be correct, so we have to change that. The REC is of course the L. So yeah. So what we need to do, it's gonna be, I mean, we just missed something there. And is that since, well, we still need that, like this thing that we erased. Where is it? On the disassembly, we're gonna still need the which doesn't, I mean, we don't need to have it there. We can just make it define here. So if we do it that way, we can just go and find out what's going on. One more time. Now this tells me that the RM, well, the mother byte is 80. Is that correct? Yes, it is. We have the REX prefix, it's 80. Now probably, well, let me see, because the table was a little bit different. Okay, I see what's the problem. Yeah, I mean, since we pitch it, now we have it not in the same order as we had before. If you remember, before we used the pitch to move in rows, and move along, you know, because that was the way of the order of stuff, you know. So right now what we have is the other way around. We have EAX. Well, this is EAX, AX, yeah. We have AL, then we have CL, DL, BA, AH, and then we have EA, and la la la. So and this, so the RM here is not gonna work if we want to do it that way. So we should, I mean, we can change it back and do it the same way, or we can try to find another way to do it, which, since we know that we have C0, it's because yeah, the encoding is like that. That's kind of wonky. I mean, the only thing that we needed to do with the table was to transpose it. Was not to transpose it, but just to skip it, you know, so to divide it into groups. Yeah, okay, so let's do that. So let's do that. You know, sometimes that's what happens, you know. Sometimes that's what happens. So oh, Jesus Christ. Okay, so it doesn't matter. We can just do the same stuff as we did before, you know. Oh my god. Okay. There you go. So yeah, and this is gonna be the same, you know. This is okay. This is the thing that we kind of kept it, you know, that way, you know. So it's just like this kind of wonky thing, but this is useful because we can use the REX as offsetting, so that's kind of nice. So what that means is that we can use this as what we had before, and this is are the other groups, you know, which is the only change. And for example, this one, since there are two tables, we're gonna go fetch register open. The way we have it right now, we don't have a way to do the difference between REX and R8, isn't it? So that's also, we have to, what is it here, we say, hey, we have that this is a group, but we are not using the memory operand. So in this case, since we don't have anyone, we're just gonna go by the table itself. Yeah, because the R bit selects R8s. So for the sake of it, yeah, we will need to also do that as well in here. So let's kind of do that. So first, let me well, this transformation will be hold the other stuff. So, and this transformation we will need some offsetting to change the base and to change the thing. So we go for the indexing here, which will be the pretty much the same case. So it will be something like this. So it could be pretty much the same, isn't it? Because you think about it, it was just the other way to do it, you know, because the offset, well, instead of doing here, we can just do it here, see? And that's all she said. So we get the offset just cleanly, and we do it this way. Because if you remember, we have AL, CL, BL, so we have the size correct. We just need to get with the info offset thing to get the right size, you know, which was the reason why we had the offset. And for the REX, we just need to define a way to encode that thing. So yeah, I mean, I prefer it this way. In that case, we just need to do that. So let's go back into here. The power of Control C. Yeah. Control C. That's it, isn't it? Control Y. There you go. So we do that way. We should compile. There you go. And here we just make this little transformation. There you go. So if we want to do it that way, in fact, well, let me move this to the place where we want it to be. There you go. It has 2 times. We just need 1 times. There you go. So this is the whole exchange. That's all we need. We don't need anything else. And if we want to get to the right one, let's say right now we get, you know, offset is gonna be 2. That means that we're gonna get to pitch, and the pitch is just the same for all of them because that's the way we code it, which is nice. And then we don't need to do anything up there. So we just need the offset on the pitch, and then we move by the offset on the table, you know, which is the case that we go that's the offset is gonna be gotten by the rec field, and that's it. That means that for the first case, you know, we have AL, CL, DL. We have pretty much this table, you know, AL, CL, DL, BL, AH, you know, and we're gonna go to the pitch and we're gonna get EAX, you know. So that's it. Okay. So let's do it. It was a tricky problem, but we just need to think about, hey, it's the same thing, but it's just transpose. So there you go. Here you go. Thanks to linear algebra. Thanks to mathematics. So there you go. We got a big scan reverse. So you remember the offset is 2 times the rectangle pitch. We should have a rec, which is AX. There you go. There you go. That was the only problem. And there you go. Push string to buffer, AX, return result. So right now we don't print the thing, or what? Oh no, here it is. Oh, no, this is the plus. Yeah, the problem is that we thought it was the index size, but this is the base. So yeah, I mean, this is the index thing, but it has not scale. Oh no, that's correct. No, my bad. I was getting confused. So EAX plus displacement, which is going to be 33221100. There you go. Push a string to buffer. There you go. Then we go and fetch the register operand. With this case, it's now 8, you know. And if it's 8, that's okay. We have an REX, it's the same way, you know, blah, 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 blah. We have the same REX. We have to fetch the mother and byte in this case. And now we are fetching the R bit, so we're gonna get the R bit, and we're gonna get that, we're gonna get the rec group blah, and the offset is the rec. And so the base, we should get 28 rec plus an offset which is 0 plus an offset which is 0. That means that we should get to R8, but we didn't get to R8, we get to RAX, and that's the problem, you know, because that's the first one of RAX. So we should just make that change, you know. So if we continue, well, and REX byte is not done anymore there. That's a little bit weird. So let's do that both as well. Let me first change that REX byte thing. And yeah, oh, okay, so we cannot assert this because sometimes it's gonna be null, which is the case. So that's the first thing, and then here we can just say, hey, whenever we go for the R bit, we also want to modify the offset. So let's just do it, okay? We're gonna get up to the places, like let's say offset rect table pitch. All right, probably this is the same here. So the main buffer is going to have EAX blah blah blah. Right here we have RDI, which is a little bit funny. Because it's one before. Let me think about it. Are in day 8. So we have here 0, 1, 2, 3, 4, 5, 6, 7. And then we move past by to the next pointer, which is R8, which is the one we are looking for. So rec table pitch, we cannot look it. That's so mad. It's so bad. Because it doesn't make sense that it's +1. So let's do it one more time. And let's get here. So the operand size is going to be 8. And we say, there you go, the composition. And the offset is going to be, oh, my bad. This is not the thing. This is not the thing. Okay. So probably that's not. Oh, okay, yeah. Our stupidity goes beyond what we thought. So we need to change this because it's not. It shouldn't be that way, you know. It's not. I mean, let me even change it here. There you go. So I don't know why do we need the invalid to be as something different, because yeah, I mean it can be 0 and that's what we want, because yeah, if not we're gonna get to somewhere that's gonna be bananas and it's just gonna be something that we shouldn't. Of course, if we want to change that, we could say that we have a null entry, you know, so we can just say, hey, you know, we're pointing to null entry or something, which we probably were gonna do, but just hold me a second. I'm gonna put here to do. Shall we add a null entry? Okay. So that was nice to catch, because yeah. So let's go one more time. Continue. Let's enter. And now we're gonna get to the same place as before, and see that the offset is gonna be moving here, and the rec is R8. Okay, perfect. So now we have R8. We don't have any immediate, because well, we don't have any immediate. So if we print the instruction, there you go. We have our instruction that we were expecting. I'm sorry. and this is a move R8 EAX 33 to 1100, which is the instruction we're expecting now. C byte should be pointing towards 48. That's nice. Yeah, that's correct. And we can deconstruct the other instruction as well. So we're gonna pass the same thing. It's an REX. This is a simple one. It's REX EAX, I believe. So we should get the same entry. Well, it's not the same one because it has the rect to mother end thing. It's an effective thing. We have a move. There you go. And we have a rect type thing. Oh, and we haven't modified the floating point instruction, so probably that's something that we want to do as well. So let's see what happens here. We're gonna fetch here from a register, and we're gonna fetch it with a effective operand size of 8. That's correct, I guess. You can see we have an REX, you know, and in this case we're gonna use the W bit. Well, the W bit we're gonna get it's gonna be set, and these bits should be all set to 0. There you go. I'm sorry. So we're gonna fetch the mother and bind, and we're gonna fetch the RM field. In this case, we don't have that, so we got just the offset. So the offset is gonna be 0. That means that it's gonna be based of the operand size of 8. So we're gonna get on the offset of 3, and this is the thing we have to change now, because now this is not the thing anymore. We do have the W bit. You know, the W bit changes the thing there. So yeah, that's the thing we are missing. So if we want to modify that thing, we have to say that and I'm gonna transform this a little bit. Now the thing that, if you remember on the test asm, we have some tests there. For example, right here we're using REX for the effective operand size. Oh, and we haven't done it yet, isn't it? Because the effective operand size is 64. So on the memory thing, we haven't changed that. So let me put it to do there. So I don't remember. Yeah, because this is the thing that we should print it out. You know. So on the memory side, so I believe no displacement can be anything. Operand size 32-bit. Where do we use the operand? We don't use the operand size anymore. That's kind of weird. Okay. So we just need that. This is gonna be that, and the size 32. The size 64. And the scale is something that is done by the SIB, so that's okay. We just care about the index size and the base size. And that's the reason why we needed to do that. For that particular case. And yeah. So that's the thing. Of course we have to pass REX here, which we have it. So since we use it here, we can just make the decomposition there, which, I mean, we can just do it once and then pass it, or do it twice, which like, if that's the case, we can just do that first case instead of passing the by, because if that's the case, I can just do this line, get REX fields, session state, EagleFly, and we just do that. Okay. There you go, that's the theme that we can do now. And let's say we are gonna start, well, here we can just do the same thing, get REX by, and as such, we're not gonna have an offset. We're just gonna say that we're going for, we have REXW, then we got 64-bit open, so it can be R8 to R15. But we have the B or the R or the whatever, we have to pitch it, you know, that's all you say. But this is the interesting thing, and is that when we disassemble this thing, which is REX RAD, what happens if we do that? This has to be a core pointer. So okay, what differs in levels of indirection from OE and A? That's kind of weird. I mean, we have this pointer, and we pass the REX by, which is a pointer. So what's the problem? Are we using REX somewhere else? Oh, here. Oh, thank you, Mr. Compiler. So we don't need this anymore. Thank you. Okay. So I was just saying that what happens if we got that instruction, you know? So we go there, and we see the array theme, Now we have array core pointer RAX 40H, you know. So this is 4CAP. This is 4C. That means that we need it expanded, you know. Okay. So now we have the W bit as well, and we have the R bit as well. The R bit hold me a second. Hold me a second. So we have the W bit and the R bit. Alright? If we have the W bit, that means that we're expanding to 64-bit operands, which is the case. And we have the same mnemonic, main operand, main opcode byte. Then we have 80, which is the case because we have REX here, and since we have 8-bit, that goes to the, so we have R, and R goes to the rec. R goes to the rec. R goes to the rec. That means that we are using R8, you know. Okay. So we're using rec. That means that we are using R8. If this was RAX, this wouldn't be 4C. It would be just 48. Yeah. No. It would be 48. And then we have REX. That REX is because that's the normal thing happening for this case. So that's what we changed within the changes we did there in here for the REXW and the memory operand thing. So the memory operand, we're gonna define it with 64-bit mode because that's the default thing. And we can just say that that's the default, so we can compress a little bit there. And yeah, the operand thing stuff, it just plays around with this stuff, you know. So that pretty much makes the sense for it. So I want to do something here. So that this is the instruction we want, you know. So probably we should change this, so I have to put it that way. And the 4040, I don't understand it, but yeah. Probably, yeah, it's because yeah, because where is it? If we had RAD, which which was the case before. Well, in fact, I can say this, I can say that. This is where if that's the case, we should expect to have, we should see that we don't have the W bit at all, because we are not modifying it, we're getting just the word, but we have the R bit set. So W bit's not set, R bit is it's set, so that's why we have the, and then we have REX, but that's because that's the effective operand size in 64-bit mode. Okay, so if I see it, this is RAD. So yeah, the only thing that changes is the modern byte. So as we see, we have R, we don't have W. The effective operand size changes not because of W. If you see here, it's not because of W, it's because of the REX prison. So, and probably because that's the effective operand size, you know. I mean, that's the thing that changes. So this is wrong. With this, we can see that on fetch memory operand, this is not correct. This should be this. And in fact, well, this is already something that we already resolved before, isn't it? That we get from the effective operand size, effective address size, sorry. So the effective address size already has the information. That means that we can just say this, and that's all. We don't need to care about it anymore. And probably in the future we're gonna pass that here, but for now it's just gonna be that way. So yeah, I mean, we don't need to care about REX fields and stuff like that. We can just do bananas. And if we do it that way, let's see what happens. You know, here's the same. It's gonna be the effective address size. If we don't have any operand thing and stuff like that, which is fine, I guess. And then now we solve for the address thing, and the operand thing, it can be solved on its own inside. So if we do it that way, the displacement, it has its own rules, so that's okay. The scale has its own rules as well, it doesn't matter. This IB by person, yeah, it doesn't matter that thing. So we go now for the fetch register operand, and here we don't care about getting the bits, you know. We get the bits, whatever they are, and we just say, well, you know, we get the rec groups, rec blah 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 blah, and fetch our own field and stuff, you know. So the W bit makes the operands go to REX, you know. It can be any, just go to REX. If we have B bit, it doesn't change to REX, but we have to add the bits themselves, you know. For example, well, let me I can add it, or first, before checking about the B bit and stuff, I have to transform the W bit stuff first. So I'm just gonna say this. I'm gonna say this. So right now, and let me change it because we want first to disassemble well, here we need both, isn't it? We need that's why we have D. So we oh yeah, whatever. So we need to add the bits. So let's do it. Let's do it. So well, let's do it first here because this is simpler. So the B bit doesn't select the size. It selects the group, and we select an offset, let's say. And we can say, well, you know, rectangle pitch. We let me see. I'm gonna say like, hey, it's just the same thing because it's gonna be the same size, you know. It's just, now I think about it, it's just the same thing, isn't it? Like, let's construct it. So we can see. You know, it's gonna be the same here as this one. Just, well, I'm gonna put it here. I'm gonna add, we're gonna have our well, hold on hold me a second. Where is it? It's not this one, it's not this one, it's not this one, it's this one. And this only uses B, but it can be R, or it can be R or B. ALCL. So we want RAL, RNAL, R10L, and for here I'm gonna change the L's for W. So probably we want something more like this. Yeah. Yeah. And we can just say, hey, on the tables, this is not gonna be normal, it's gonna be general purpose register, general purpose register, GPR. And then we can just think about, yeah, because this table is like the kind of the thing, you know. Of course they are available in 64-bit mode, but they are not we need the REX thing, you know. So that's the reason why we have to have that thing. So this is kind of funny, you know. REXW is gonna be now different, you know. We're not gonna change the group anymore. We're just gonna say, hey, the offset is gonna be rec table. It's gonna be 64. And so you see here, yeah, we're gonna have just things 8 byte word or 64, and they're gonna be 8s, you know, 8 blah 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 blah, which I think is good. I like it. A table of 64. And it depends on the bit if we go to the other one or not, you know. So we will still need to have to use the bit scan reverse for the size. Because let's say these are, well, I'm gonna call them GPI, and these are gonna be extended '64 or GPR 64, I guess. And this can be wherever we say that we have a pitch. It's gonna be rectangle pitch times 3 times 4 minus 1. Yeah, there you go. GPR 64, we're going to 64. And here we are going on to, it depends on the size. The operand size attribute is going to define that, but we can just have another table and do the same stuff happening there. So that means that this is okay. Here we don't need an offset. Here we don't need this. Here we don't need this. And here we don't need to. This is something that we don't care right now, but yeah. And this we will need to do it as well. For the 64 ones, so we get the offset to the pitch, whatever. We get info from the base, you know, we move from the base to the group. When we use the pitch to move across the to the register that we want to go, and the offset just comes along. And for the offset, we will need to use the same stuff, isn't it? So we will need an offset here to use it. So now it's just this, you know, we just change the table and that's it. And then I can say this, so it's more like the thing we want. And then over here it's just gonna be the same stuff. Alright, compile. And this is GPR 64, same. And it seems to work. So I think that's it. It was a little bit confusing, but we are getting somewhere now, because we didn't understand what does the REX prefix did by itself. So that was the hardest part to do, but let's see what happens now. So I think that's good. We added the other entries there, and we have to add, well, we have the, on the tables we have the GPR 64, the control debug. We have to change the size, so let me move it on the initializer. Where is it? Initialize, there we go. So this is gonna be 5 times A as well. Well, it's, how many they are? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There you go. 4 times A, 1, 2, 3, 4, 5. And now we're gonna have on the tables, we're gonna have pretty much rec type GPR64. This is gonna be MMX, XMM, control, debug, and FB. Okay, there we go. And as well, we got that we have the register type. We probably want to change that as well. Which is something that we use now. We can make it add to the entry. Yeah, normally right now we don't use EVX, but in the future we're gonna add here like a bunch more, depending, like XMMM, YMMM, CMMM, etc., etc. So they're gonna be adding in here. So probably that this is gonna be looking pretty much similar to these tables. And these control things, we cannot, well, they don't follow the pattern. They do follow the pattern just for one row, let's say. So if we need the rec, we can use the rec. It's a little bit wonky there, yeah, I know, because we don't use the RM field. That's the crazy bananas thing about the floating point. But yeah, we don't care about the floating point instructions right now, so I'm gonna just keep it that way. It's gonna be bananas, I know, it's not gonna work, but let's see if the first part works. So we're gonna go with the same stuff. Now let me see the disassembly state, because probably that's something to see here. Rec groups, we're gonna have GPR 64 MMX MSMMN control debug floating point. Okay, this has a base blah blah blah, count blah blah blah, the count blah blah blah, base blah blah blah, the XMMN, this is XMMN, count save for EA. Alright, 50, that's correct. Control 58 and FP 60. Okay, we have 68 now. Table REX, we should have the same idea here. ALCL, DA, DLBL, AHGH, DHH, AXCX, blah 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 blah. EX, CX, CDX, CX, blah blah blah. ESP, PSI, RX, RSP, RBP, RSI, RDI, RAL, R9L, blah blah blah. R10L, 12W, W, DD. Can probably move these a little bit so I can see them. DDDD, DDDD, R9, R15, MM0, MM1, 2, 3, XM0, XM7, 0, 0, 0, 1, 0, 2, 0, blah, 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 blah. Okay, that's pretty nice. And probably, well, we haven't gotten to the well, yeah, that's correct. So that, yeah, that's good. We're gonna pass the byte, there you go. REX byte, we're gonna fetch the memory here with the index size of 8. That's correct. Now I was forgetting it, but yeah, the instruction that we are, did we change the instruction at all? We didn't, isn't it? So we need this instruction. We are looking for C A P. First we're gonna do this one, and then we're gonna do the other. So this is for C A P 8000, and this is the same stuff. And then we're gonna do the other one, which is this one, 44AB 80, and the same stuff, which is just changing R8 there. And then we're gonna do the other one, and then we're gonna do the other ones, okay? We're pushing, man, we're pushing on REX. All the REX possibilities possible in the oh, okay, so but we're adding this entry, so hold me a second. Because, well, it's the same, because it's the same by, so it should be okay, isn't it? It should be, because it's the same entry. We don't need another entry here. The only problem is that the mother and by has to define everything for this particular case. Array core pointer REX plus 4 or 4, okay. And the other is a dual pointer REX 4, okay. So yeah, I think it can work. It can work. We just need to define them, and the entries are gonna be the same for this particular case, so we don't need another entry for that. Alright, let's compile. Let's start with this. Alright. Entry, get mnemonic entry. What about the entry? Is the one we were expecting. Operation mode, yeah, that's correct. Effective, operand count, mnemonic count, yeah. Rec type, we're gonna use the rec type right now, so that's okay. Begin operand instruction, fetch memory operand. Let's go enter here. Displacement, we don't have it, say B. Index size, it should be 8. That's correct. And we have RAD, which is not correct. Hold me a second, another time here. And the reason is that if we go here, we get the REX fetch, and then for this particular case, REX has bits W and R set. You know, we don't have the B bit at all, so we shouldn't go for the GPR64 group. And the offset is going to be 18. Which and the table, where's it? Yeah, we have GPR. Okay, we have GPR. Which is the default right now. Yeah, we have GPR. That means that we're gonna reverse the 8. And we got the info with an offset of 3. That means that we are already moving 3 in that sense. So okay, so we don't need to do this thing right here, because we're already doing it with the big scan reverse. Okay, so that's good, because we resolved it before. Okay, so that was the confusing part. So we should just do, where is the W bit? But just to make sure, because now the mixing is a little bit weird. Since we're doing that part, I'm gonna do it in the other side, because yeah, I mean right here, if you remember, we say that we have REX present, and we just copy the by. If we go for REX present, we just say, hey, the bit is on 4F0 for F, and that's all we do. We don't do anything fancy there. So we copy the by, then we change the operand size override, which we don't do anything at all right now, and we just say, hey, we have the data size to 82-bit. But this is not correct at all, because the thing is that it's not gonna be 64 unless the W bit is the one that's so it's more like this. It's just if we happen to do this in here, then we change the whole story here. So REXW is gonna make the change to 64, Now let me go back to the REX thing. Look at this. If it's 164-bit operand size, if it's 0, the operand size is determined by CST. That means that here, the code 7 descriptor, we have this, So if it's 0, that means we are looking at like a 32-bit table operand size thing. But if we have REXW, then we're looking at this table. But look at this, if it REXW is 0, we have this table. We're not looking at the D flag on the segment descriptor. So what that means is that REXW is going to promote the operand size attribute to 32, sorry, to 64. So that's the reason why we have 64 here. Otherwise, if we don't have it, we have an operand size prefix. You know, here we don't see the comparison between these flag encode, segment descriptor, and stuff like that, which we don't care right now. But we can just say, hey, we have we don't have it. We can just say that we look at the operand size prefix and stuff like that. So that if we say something like this and say we have the W, then we have 64, 64, and then we have address size of right prefix. This is gonna be, this is the thing that we have here, isn't it? We have W. It doesn't matter if we have that. We're gonna have 64, 64. The address size in our case is gonna be 64 or 32. That's correct. If we don't have the W bit, then we'll have 1632. Okay. If we have an operand size override prefix, then we go to 16. If not, we go to 32. If we have another size override prefix, we go to 32. If not, we go to 64. So this is correct. The only thing that was the problem was the W bit. We needed the W bit to get compared. That makes sense. So I think that's all. And now let me drink water. So if we do the check in there, then we go to fetch register operand. We get this. We don't need that anymore. We're resolving it upfront. And this is the, this is this table for 32-bit. It's another table, but yeah, we have to make it to do there. Let me put to do. Well, right now we don't handle the override prefixes at all, but yeah. So yeah, that's the whole story. So let's go back. So we got the REX, and in this case we have WR, which is was expecting there, and we move along. Get the mnemonic entry. We see that it's correct. We say, hey, what's going on here? Yeah, we have some magic going on here. 103 blah 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 blah. Move mnemonic name. Okay. Mnemonic name. Okay, perfect. Begin fetch memory open. Let's see what happens in here. Probably we have a breakpoint somewhere here. Yeah. Now the index size is gonna be 8. That's correct. There you go. Now we have REX as we were expecting, and now we can push it. The displacement, which is 33 22 11 00 plus blah blah blah. Okay, that's the mnemonic for the memory operand. Let's go for the register one. We got an effective operand size of 8. That's correct. Okay, then we can go and do the same stuff here. Got it. Fetch and fill. We're gonna get the R bit. We got, and we're using the R bit. Oh my god. Okay, that's also busted. Like what? Yeah. So we don't need this anymore because we got the REX. So this is gonna be REX B, and we need REX R. There you go. There you go. Fetch immediate operand, we don't have that, okay. So there you go, now we have a correct instruction set. Now move R8, REX plus 3322221110. Alright, so let's go to the next instruction. The next instruction should be RAT, RAX plus blah 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 blah, okay? So let's do that as well. We're gonna get it. We don't have a W bit here, so we're gonna use these operands. Then we're gonna say, hey, we got the mnemonic. What about the mnemonic? That's the same mnemonic. Alright. And then we say, well, you know, we're gonna go to the same stuff here. Fetch register operand. In here it should be the same idea, I guess. You know, we have REX. There you go, we have REX, that's correct. We got the same displacement, so we should expect to see the same stuff there. Boom. And here, this is the magic what happens. This is where the difference should come about. This is where the effective operand size is 4. You know, this is 4. So this is gonna be different. We got there, we have there, fetch model RAM, RMFib, fetch RMFib, we don't got it. We got the RFib, we got to the 64.1 files of rec, there you go. And then we say, hey, what's going on here? Big scan reverse for the operand size, we got the info. It's gonna be, the offset is gonna be 2 now. We should go for the, let's see what's going with the rec. We have RAT, perfect, that's the one we're looking for. Push and abstract, there you go. And then that's the thing, we don't have that, we print instruction. There you go, now we have RAD, RAX 33222110. That's the thing we were expecting. Now let's go to the other instructions as well, so we can print them out as well. I don't know which CPI we are at. Now we're on 48. It's a REX as well, but this is simple. It's just something like REX something. I don't know. Okay, let me see the stream by thing. We have this, and this is this, and this is like that. So we don't have this one right here, or at least, yeah, because we are on 48, that means that it's REX. So that means that we're not gonna print this one, we're gonna print this one. So yeah, we're going to print move REX, okay. So just to know. There we go, we have an REX, we have a W bit, that means that we have to have the operand size override. We got the mnemonic, and this is the other entry, which is the 1-1 stuff. It's just the same move. Begin operand extraction, there you go, fetch a memory thing. RX by, it should be what? Oh yeah, okay. Yeah, that's correct. We can go into here. We can. Oh my god. Here. Oh my god. Oh my god. Yeah, we do have REX. This is the one that goes on REX, which is correct. Well, since it goes from rec to motherm, we're getting here the motherm by. Okay, let's see what happens on the other one. And this is the buffer size. This is 8. There we go, RDX, push string. Go fetch immediate, and we print it out. REX, RDX, alright, perfect. Alright. Move REX, RDX, REX, RED, okay. Okay. And what else? The reason was because we're going, rec to motherm. So we're going to fetch the motherm, which has REX, but it's going from rec to motherm. Okay. Yeah. That's the reason. So what about cbyte now? We're on 80. That means, yeah, we moved from 48. Now we have 80 there. This 80 instruction is an add. It's an add EAX FFF0 OP. Okay, I believe. There's no REX prism. That means that this should be something different now. So let me change it. I mean, it's gonna work, but this is not gonna do it anymore. So probably what I was thinking about is this. Now the operation mode probably is something also to think about. It all depends, because at least from the tables, to get to 16, I mean, the only way to get to, I don't know, we have to read about real address mode, because in real address mode it's gonna be something different, the sizes and stuff, you know, because if we target is 16, for now we don't care, but I can have something like initialized for now, which, yeah, I mean, this is better, I guess. So now it's just alright. Now probably this is not the case if there's no REX prefix, or because if there's no REX prefix, what's the data size information? Normally in 64-bit mode it's gonna be something. So yeah, I mean, this is a little bit quirky, but yeah, I prefer the way we have it before. So this way. Oh, let me go back. Yeah, it's a little bit more understandable. There you go. So for now, we're gonna say, hey, we have 64, no, 32, 32, and the initializers, and then we're gonna go out and set that thing. We go modify it, stuff, whatever. If we use the prefixes or not, whatever. So yeah, I like this. I'm gonna put the data. Well, I already have the operand ones, but you know, test more operation modes. Yeah, that's better. Okay. Dun, 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 dun. There we go. We have the basis of it, yeah. REX. This should be the same. Alright. There we go. We go for the next round. And we'll see what happens. REX. RAT. And we put it out. And it's the same stuff. We go for the next instruction. It's gonna be on REX, RDX, per instruction, REX, RDX, perfect. We go to the next instruction, let's see what it is. We don't have an REX present, we go for the entry. It's an add, there you go. Fetch modern bar, begin operand instruction. You're gonna go and fetch operand, fetch register operand. In this case, we had the index size of 8, and we wanna get EAX. So the encode, yeah, that was a problem because this was buggies because the way we got it now, it should be REX, you know. So that's gonna be correct because now it's gonna be REX and stuff will be immediate stuff. So yeah, just to mention it because this is what it's gonna get. Fetch and fill, offset RM. We got there, we got the rec, and it's REX, that's correct. Push string, and then displacement, index symbol, push string to buffer, and then displacement stuff F00. This is just the same stuff happening. We have REX plus something. Now since we are on REX, oh my god. Oh, okay, so good because it's using the index size. So yeah, this is good. That's correct. We have the F0. I was like thinking, yeah, we needed to do that, and then we just happened to have it. That's kind of funny. Okay, so yeah, we have now, yeah, because the displacement had to be sun extended to the size of the effective address size, which in this case is our index size. So that's correct. Got the displacement, and we got for the register. I don't know what's going on there. We don't have a register, that's correct. And the immediate buffer, let's see what's going on. We should have an immediate buffer, which is something. Print instruction, there you go. REX FF0 OB, there you go. That's correct. We have add REX blah 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 blah. Yeah. So the next instruction is, this is incorrect. We need FF there we go. 1 2 3 4 5 6 7 8 9 10 11 12. There you go. The next instruction is a fat st0 st1. This is where the magic is not gonna happen, and yeah, there you go, there you go, there you go. We got an entry. It's a fat, that's correct. We begin, we don't have an REX in this case, that's correct. We're gonna fetch it, we're gonna see what's going on here. Of course it's a raster. And here, well, we have a zero parent size, it's a floating data size, FDP, FDEP, FDP, okay. I mean, it's not like, oh, I mean, we already have like a difference there, you know, for in double extended precision, yeah, flow double extended precision. Now I don't know why it's double. Oh, okay, yeah, I got it. I get you. So it's gonna be FDP, which is 80, and and this is gonna be bananas. Okay. Get REX fields. Fetch remove fetch and fill. Because here, of course, we don't have the reg and rm stuff encoded, you know. So we're gonna get the offset. You know, we need type. We need a valid type to be happening there. So, well, actually, we got the reg. Well, we don't have the reg type yet. Yeah. So let's do that because I liked it. You know, get the type. So let's add it here. We got the RX good, so let's go and solve for these things that we got before. So it's not particularly difficult, but you know, we can just say let's go one by one because all of them it seems to be needing that information. So I will start with here, and this is gonna be rec type, and this is rec type GPR. Normally it's gonna default to GPR. Nonetheless, because that's something that we don't know for this case, you know. Yeah, I don't know if there's some coding that tells us something about it. I don't think so. I mean, over here when we got to the place, it should be D8. This is a floating point instruction. So this D8. Remember that the floating point instruction, if you remember, let me go a little bit here. It has a different format, and it's like saying, hey, this is the thing that we should follow, which we don't do right now, and that's the reason why we have the problem, which we should, of course, to do that. So for now, I'm just gonna say that we're gonna keep the indices, which I erase. But yeah, probably the type or something else. I mean, there's not a lot of difference, if we use the type, we'll need to solve which one we got. But since the instruction is the one that is telling us about that information, I mean, it's not coming up from just using the REX prefix or stuff like that. So yeah. So I mean, it's just, I mean, we still need the indices. So let me go to the table thing, mnemonic entry there, and I'm gonna say, hey, you know, we happen to have this stuff, and we happen to, well, I was thinking that probably the register tag was something there. Probably it's not necessary, you just need an index 4 now. Probably later we're gonna happen to use it. So I'm gonna do that. And here we had something before here, like entry register index. Now I remember how we did that before. It was like the register index A or register index B. Well, I'm gonna keep it, it doesn't matter. Now I don't know if I can use REX prefix with floating point instructions. It shouldn't make any difference, isn't it? I mean, it could be, but we don't care at all. So we just say for now I'm just gonna say, I'm sorry, rec group rec type, sorry, rec group type equal rec type FP as we do all this stuff. I can say have the rate entry register index thing. For now I'm gonna keep it, it's okay. And the thing which gonna use that is, I don't remember, and then it was fetch rm field, isn't it? I guess. So this is gonna be offset now. So that's particular case for them. So that info offset is just gonna be nothing plus an offset there. Red offset A, red offset B, red offset A, red offset B. So if that's the case, let me go to the init and I'm gonna add it as well. And it has to be, where is it? Bound, move, shield, be aligned, be and resume, and FLD forgone. Here you go. And this is FB, and this is FLD. This doesn't have register A, register B stuff, so probably, well, this doesn't need that because the rec type should be invalid, I guess. Yeah, but for the forgone, yeah, it should be FB. And index A, rec offset A, rec offset I don't remember if it was this way or the other. Since we're using, let me see, rec to mother and we said it is true, that means that and the mnemonic is moving from, I mean, in fact, well, now I think about it, well, I'm gonna keep it that way because whatever. This is the path, and yeah, because this is, I mean, in standard assembly this is not correct, but I want to keep the two operands, so they're gonna be explicit. Later we can change it to the standard if we wanted to. So this is ST0, ST1, so that means that one is gonna go first. We're gonna, so this goes on the rec, and this goes on the RM. So first we're going for the RM, and then we're going for the rec. Okay. Okay. We can use the same thing here. Fat entry, fat entry, fat entry, and the fat entry is just the same. Oh, well, this is the same, and this is the other way around. The forgone, well, both have true. That's interesting. In this case, it's not gonna work because we need the indices. I don't know why we have direct to mother end, because it's not a special case here, but well, let me just say that it doesn't matter. We're gonna change this in the future. This is correct. This is 0 1 and this is 1 0 for the FUCAM. And then I fill this 0 4 4. That doesn't care about this. Optimal word, blah 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 blah. Mid size, restore price. Okay. P line R, XMM 0, XMM 1. This doesn't care. And that's it. Okay. There we go. So I wanna run this a bunch of times. This is the move. I don't know where I am. I don't know. We are on the app, that's okay. We are on the FAT, okay. And yeah, we're on the memory. We have an effective operand size of 4. Well, we don't care about that. Where's the operand thing? And we are fetching the arm field. That means we're going for the A. And the B should be 1, okay. That means that we're going for the base 60 and the REX should be ST0, that's correct. Okay. And here we have ST1, that's correct. So we have fat ST0 ST1, fat ST0 ST1, that's correct. Let's go to the next one. Here you go. We're gonna get ST1 ST0. There you go. There you go. FUCAM ST1 ST0. FLD, let's go for the FLD as well. FLD. Okay. So where we go, REX present, get mnemonic, FLD, fetch memory operand. I don't know what's going to happen here. Yeah, it's a memory thing. Index size invalid. We have an SIB. We don't have that. That means that the buffer is just nullify. There you go. And then displacement mother and by it's just something that we got there. Now, since the index size is positive, this is we have a problem here. That is that it should be, well, I guess so. I don't know. I think so. I mean, the operand size override thing. Right now it's 04, but it should be a whole operand thing, you know, a whole displacement that is sun extended. But yeah, because the index is just busted. Well, this should go like well, it's because the displacement has to get the data. If we wanted to sun extend it, that should happen from the base up, because right now we just sun extend the ones that are 8 bits to a normal thing. We don't sun extend the ones that are 32 bits, so we can have that as a to-do, but that's okay. Now we're gonna fetch register operand. It shouldn't have anything at all. There we go. So we put instruction. There you go. FLD blah 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 blah. Let's go to the next one. I don't know what it is. It's VM resume. There you go. What else do we have here? P-align R. Let's go for a P-align. The P-align R is just going to be busted because we didn't set the types, the group type. So let's go and do it. So you can get it, at least for now. We're gonna get an offset for XMM0 for the REX field environment. So now that we are on XMM0, and the way that we do it right now, we need to change a little bit the thing. We can use the same indexing stuff, and that would save us for different data information, which I guess is gonna be the thing. I guess so let's change that as well. We just have one instruction for that case, so for now it's gonna be okay. So it's gonna be P-align R. I'm gonna say P-align R entry, P-align R entry, P-align entry. It's gonna be XMM, and it uses XMM0, XMM1. It doesn't goes from rec to mother RAM. It goes from mother RAM to rec. So that means that we have to mother RAM rec. Okay. That means it's something like that, which we don't care right now. I mean, it can be, if that's the case. I mean, we shouldn't care about this at all. I mean, because we're not gonna use that, I guess. Right now we are not using it, so it's gonna be pretty busted. But yeah, it's gonna do bananas. But yeah, it doesn't matter. It doesn't matter because the idea is just the same. So let me well. So yeah, let me just compile. There we go. See what happens. See what happens. Here on add. We're on Fucom. FOD. Now I believe, yeah, we will resume. There you go. So the entry is, oh my god. Okay, this is not what I was expecting. Oh, it's because it's not initialized. Okay. I was like, what's going on here? Pre-aligner. There you go. XMMN thing. We got an XMMN thing there. You know what I mean. So let's go and see what happens. Well, it's not gonna work because yeah, it's not gonna be a flying point, so it's gonna just think we got a mother end thing, which is not gonna work, of course, and it's just gonna tell me that, hey, you know what happens. We got for rec type, and we need the index and stuff. So the rec is just gonna be so the offset was correct or what? Well, in fact, we didn't need that anymore. Well, we didn't need that because we can still use the XML1 thing, which is a little bit funny. Okay, that's super funny. That means that we didn't need the indexing because we have the RAM rack. But I mean, the reason that this is useful is because we have a mother and byte that tells me something about that. But whenever the mother and byte doesn't tell me anything about it, then we have a prime. Yeah, so that's the reason why that's why it works, So XMM0, XMM1, 8. Yeah. So let's continue to the next instruction. This is a shield. What's going on here? So the shield is blah 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 EX03. Okay. There you go. And we have at EAX. Okay. So there you go. We have our stream back into fitness. Boom. And that's all we did. That's nice. So now we can, I mean, we starting to handle REX prefixes better, and 64-bit mode as a whole better, which is good. We still have some caveats, well, some problems with displacements, which we have to think about if these ones have to be displacements. They have to be extended to 64-bit since they are 64-bit mode. That could be the thing. If we can do it trivially right now, just changing it out, changing, well, adding this extension stuff, but yeah, we have that for this one because this is one 8-bit thing. That's why we extended it. And then the other stuff is just pretty much the same. Yeah. Hell yeah. So let's see if we can do that. It can be super simple. Fetch memory operam. Over here, you remember if it was an 8-bit, we use this thing to send extended and then print it out. So we can just do the same thing here. And say that, well, this uses the index to move the thing. Since this was just a byte, and 0x0, then we have a sign bit. If it's a 32, in this case, yeah, we have to think about how to do that. Well, I'm gonna do it. We're gonna do it tomorrow. I'm gonna put here to do it. Extend to effective address size. Alright, so yeah, that's it. And yeah, so I would say thank you very much for coming. Please, if you have any questions, post them on Twitter or YouTube and I'll be there to answer. Okay, please make relative the questions relative to the thing we did today so I can answer them. And yeah, so I would say thank you, and I will see you all on the next stream. Take care.